Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about torque and the axis of rotation. You'll recall from our previous discussions of torque that the torque is determined based on tau equals r cross F, and that among other things this means we must determine a value of r that's based on our choice of the axis of rotation. We also discussed how a system in equilibrium requires that there be zero total torque. So the question that should be posed is, does the torques being balanced depend upon choice of axis? To answer this, let's consider a simple calculation for a system that's maybe in equilibrium given one set of axes, and then choose a different axis and see if it's still in equilibrium. Now, in my previous lecture, I introduced the conditions of equilibrium, and we solved for the force of tension and for the location that the tension must be applied at for a meter stick, 100 centimeters long, given a mass of 105 grams for the meter stick and an additional weight 85 grams mass that's hung 90 centimeters from the end. And what we found was that from that same end, the tension point must be about 68 centimeters and the force of tension about 1.862 newtons. So the question here might be, what if we took the other end as our axis of rotation? Okay, under those circumstances, this becomes 10 centimeters to the hanging weight. We have 32 centimeters to the tension force, and we would have, again, actually 50 centimeters to center of mass. So, question, do the forces still balance? Well, that one we know the answer to because we specifically found this force of tension by finding these two forces, adding them together, and saying that the forces must balance. So the force part should be balanced. So we have established that the tension does balance with the two other forces. So forces are balanced without regard of where the axis is. The question is, are the torques still balanced? Well, we know that the sum of torques must be essentially r center of mass cross Fg stick plus r to the hanging weight cross with F for the hanging weight plus R to the tension cross F to the tension. So if we do this for the new coordinate system, what we have is R center of mass and Fg center of mass. Note that that is, for this system, a negative torque. So I have negative 50 centimeters times 105 grams or times 0.105 kilograms as the case may be, times 9.8 newtons per kilogram. And then to that I have, for the weight, also a negative total torque, so minus 10 centimeters times 85 grams, which is 0.085 kilograms, times 9.8 newtons per kilogram. And then the last one is a positive torque, and so we would have basically 32 centimeters times the 1.862 newtons. And that would be our new torque for this system. So we can put these into our calculator to get total torque is this number and this number subtracted from this number. So 59.584 minus 8.33 minus 51.45. And what I end up getting is actually a negative but small number. My sum of torques here is approximately negative 0.196 newtons. But we have to remember that this number right here, this last number, was actually calculated from some rounding. that I actually did not have 68 centimeters or 32 centimeters, but that was rounded from 67.8947 centimeters. And so this 32 centimeters is really 32.1053 centimeters, which when multiplied by 1.862 gives me 59.78 of some additional digits. And if we subtract from that our 8.33, and if we subtract from that our 51.45, what we end up getting is 0.0000686 Newton centimeters, which is definitely within round-off error of simply being that the sum of torques is 0. So our choice of axis doesn't matter other than that there may be some round-off errors introduced. And this works as long as you have a system in equilibrium. This means that we could choose any axis of rotation we want. And so there's like an entire set of problem-solving strategy that goes into this, like essentially saying maybe it's a better choice to make the axis of rotation be at the location of some unknown and also unneeded to determine force. So that's all for today's video. Thanks for watching. Hope you learned from it, and I'll see you in the next one.